Alright, today's 8.3, and we're going to talk about radioactive dating, or how we found the absolute age of rocks and fossils, and how we can use absolute age in finding and estimating relative age. So absolute age would be the number of years since the rock layer formed or the fossil formed, and it can be used to date fossils and igneous rocks. We don't find fossils in igneous rocks because igneous rocks are formed from very hot magma, so they would destroy anything that fell in that hot molten lava to be buried. So the fossils are going to be found in sedimentary rock layers, because the sedimentary rock layers are made of small pieces and particles that get cemented together. And so the fossil can fall in those pieces and particles before it gets cemented and then get buried and preserved. Sedimentary rocks are not effective in radioactive dating because they are made of small particles, so measuring the radioactive particles in the tiny pieces doesn't really give you an accurate time. So but fossils and igneous rocks, which the igneous rock could be above the fossil, it could be the rock layer below the fossil, it could be the intrusion that pushed up through the rock layers, and so they can give you some relative dating for the fossil and the sedimentary rock layer. Henry Becquerel is the one who figured out that uranium was losing particles, and he did it with old photography plates. If you think about how X-ray looks, a very large plate, he put a piece of pitchblende, which is a rock that has uranium in it, wrapped it up in some dark paper, set it outside, and then when he developed the plates, he could notice that there was something being emitted, some type from the uranium. And what later discoveries by Marie Curie, Einstein, and lots of people working with these radioactive elements and the math of these radioactive elements figured out that they are losing particles. They are losing protons and neutrons. They are losing energy. And when an element is giving away protons, it is changing to a new element. And so the radioactive parent is going to keep losing particles till it becomes stable. And that stable daughter isotope is going to be a different element if protons are lost. And so what we found, or what they found, is that there's a certain amount of time for each radioactive element to lose particles, and they're going to lose particles approximately by half. So if you've got, say, a 50-gram sample, and it has a half-life of 2,000 years, then over 2,000 years, that 50-gram sample is going to become 25 grams radioactive and 25 grams stable. And then when another 2,000 years passes, that 25 grams that's still radioactive is going to be approximately 12.5 grams that's radioactive and 12.5 grams that's stable. So it's going to keep decaying by half, and that's what we call half-life. Potassium and argon dating can be used to measure the age of igneous rock, and then carbon-14 and nitrogen-14 can be used to date fossils. Now, fossil dating is only going to go back to a certain number of years because the half-life of the carbon and the nitrogen is not very long. For carbon-14, it's 5,730 years. And so dating something that's really old, like 3 billion years old, there's not much radioactive element left, and so the mass spectrometer and the other instruments that use and have a hard time detecting how much of the element is still radioactive at a certain age. So if you do the math, when you've got half radioactive element, half stable element, that tells me one half-life has passed, and I got a 1-to-1 ratio of radioactive to stable. When 2 half-lives have passed, so another time period has passed, I've now got a 1/4 that's radioactive and 3/4 that is stable. And then notice the ratio matches what my numerators are. Then when the 3rd half-life passed, I've now got 1/8 is radioactive and 7/8 is stable. And another half-life passes. We're on half-life 4. Now it's 1/16 to 15/16 stable. And you keep going. So we get down to 6 half-lives, and we've got 1 in 64 parts are radioactive, and 63 in 64 parts are stable. We can go to a 7th half-life, and it's going to keep increasing the amount of stable and decreasing the amount of radioactivity. And if I multiply, say, 6 half-lives, and the half-life was 2,000 years, then 6 times 2,000 is 12,000 years old. So when you find a igneous rock that has 1 part radioactive and 63 parts stable, and that element had a 2,000-year half-life, I know that that rock is 12,000 years old. So that's how they do it. And radioactivity is, I like to say, the gift that keeps on giving, because with math, I can keep getting smaller and smaller and smaller fractions that are radioactive, but I'm never going to get to 0. Now, another way we've talked about finding out about the environment with time is core sampling, and we mentioned that and there's 2 types of core sampling. We talked about earlier this week about ice cores. There is also mud, and you go to, say, Crater Lake, which is in the top of a volcano, and remove a core of mud. You will find evidence of the past life as well. So core sampling is looking for, in ice, is looking for trapped dust, ash, gas, and radioactive particles. Cores of ancient mud are looking for, again, chemicals that are present, or their fossils that are present in the core sample. So core sampling is another way that we can look and try to find out about ancient times. Now, what we're going to do together is we're going to do the 8.3 section of your changeover time packet together. That should still be out. We just checked it a little while ago. And we're going to do those problems, I think it's 29 through 33 together. And then we should have this part of our packet complete.